Welcome to the course on two-dimensional signal processing, principles and practices. We are doing this 2D Fourier analysis. In the last lecture, we had done the DSFT, that is Discrete Space Fourier Transform. And today we would like to know about this 2D DTFS. So DTFS is 2D Discrete Fourier Series. So this is generally used for the frequency domain representation of the periodic sequence. So as we did in the 1D Fourier series, for one-dimensional periodic sequences, would do that for the 2D Fourier series as well. And as we know that periodicity x of n1 comma n2, for that, if n1 and n2 row-wise periodic or column-wise periodic, if the period is n1 and n2, what is the condition we had already looked into, and we have seen with an example how this repetition in the pattern of row-wise and column-wise also. So x tilde of n1 comma n2, here we tilde, we mean it here is a periodic sequence. It is a repeated pattern. Repetition or a repeated pattern, x tilde n1 comma n2, x tilde n1 plus n1, this is row-wise periodic, equal to periodic in column wise also, n2 plus n2. So for all values of n1 and n2, if this condition is satisfied, the 2D signal is periodic, where n1 and n2 can be n cross n as well. Both sides row wise and column wise can be equal period, or it can be a different also. So this case, this x tilde n1 comma n2, r1 minus n1, the powers minus n2, is not absolutely summable for any r1 and r2. So this condition, so this doesn't converge, this converge for a periodic sequence. So we would see the convergence of the signal for that the Fourier transform exists or not in all these details. But right now the periodicity can be extended, and this full periodicity, how does it help in DFT as well, we'll see. In this case, so the 2D DFS, this time is already known. Here in the case of two-dimensional, we remove the time and we use the space. So DSFT, if you also see the 2D DTFT and use it as a DSFT. So here simply this 2D Fourier series is taken as discrete Fourier series. The time is dropped here, and if the analysis equation which is obeyed by this DFS, just simply extending the 1D DTFS, what we had done in 1D, the time is dropped here, it is DFS. So x tilde of k1 comma k2, this tilde we use it to represent the periodicity in 2D. n1 varying from 0 to n1 minus 1, the summation. Similarly, n2 summation also varies from 0 to n2 minus 1. These are the periods. X tilde n1 comma n2, e power minus j 2 pi k1 n1 by n1, this is capital N1 here, and e power minus j 2 pi k2 n2 by capital N2. And this is discrete sequence, so needs the summation to get into the Fourier domain. So similarly, for the synthesis equation, once we know the coefficients from the signal, we found that coefficients, if you know the coefficients and can get back, this is the inverse Fourier series, where x tilde or the signal can be represented in terms of this k1 varying from n1 minus 1, k2 varying from n2 minus 1, x tilde k1 k2, this is a Fourier coefficient, and then e power j 2 pi k1 n1 by n1, e power j 2 pi k2 n2 by n2. So here it is the synthesis equation. You can see that how we get the coefficient back from the coefficients also. So properties generally obeyed by the Fourier series. What are the important properties we will look into, and we'll see some examples of these properties as well. X tilde and y tilde are two-dimensional sequences, x and y, and these are periodic with n1 and n2. So the x tilde is periodic with n1 and n2, and y tilde is periodic with n1 and n2. Then its Fourier series would be x tilde k1 k2. You can note down that the x capital in the Fourier domain, or in the frequency domain, we represent this as a capital X, k1 and k2 are the Bind indices. Also n1 and n2 are the time indices. Small x is representing the signal in the time domain, and also we use the square bracket to represent it in time domain, and the parenthesis is in for the frequency domain. This is for x, and for y similarly, if these two are the 2D sequences, y tilde k1 k2. If this is the case, n1 and n2 are the periods of n, this capital small n and small n2. So the DFS is assumed for this n1, n2 and IDFS as well. So you can get back the sequence. So the arrow mark both sides of the implies that you can go from here one forward, and from the coefficients you can get the signal as well. So the first property is it's linear. Its linearity property is we have seen already in 1D and other DSFT as well. The case is that the superposition and homogeneity. So if we have this scaling of one signal and scaling the other signal and sum it over and take the DFS here, then A into x tilde of k1 comma k2 plus B into y tilde k1 k2, that is the individual DFS scaled by A and B here, and the summation here. So if we add two sequences and take a DFS, that would be again a summation of DFS of individual sequences. Also the scaling applies to it. So superposition and homogeneity properties are helpful in to find to use this in the applications. And there is a property 2, periodic convolution, in which this is the convolution we had discussed in length, but the thing is the linear convolution, and we have called it as circular convolution. Here this is same as this circular convolution. The periodic convolution is the circular convolution. Here the sequence is periodic. So x tilde and y tilde is circularly convolved. So note the difference in the notation of this convolution. It's not only asterisk, the circle with the asterisk. So it gives it that multiplication in the frequency domain. X tilde and y, x and y are these capital K1 and K2 are the bin indices. So this what is a circular convolution? We mean L1 varying from 0 to n1 minus 1, L2 0 to n2 minus 1 summation. X tilde, this is the changing the indices, time indices to L1 and L2. So we did this similarly for the K1 and K2 in 1D case. So that's the same thing. We have using K1 and K2 in the frequency domain. So we just use the notation L1 and L2 here, and y tilde n1 minus L1 and n2 minus L2. So this summation varies only for a particular period, that is n1 and n2. So 0 to n1 minus 1 and 0 to n2 minus 1 is this summation. It's not varied for all the length of the sequence. So it is varied only for the periodicity of the sequence. So this is a circular convolution, and the multiplication, if we see the time domain multiplication, that is again the circular convolution in the frequency domain. So we can go from one domain to another, that is time domain to frequency domain and frequency domain to another. So the convolution is multiplication, and multiplication is here convolution, that is a circular convolution. We should keep in mind this is not a linear convolution. So now coming to the expression of this, as obviously in convolution in the frequency domain, it is x tilde of L1 comma L2, K1 minus L1, K2 minus L. This is also varied for a period of N1 and N2, and the scaling factor 1 by N1 comma N2 is used in the frequency domain. So the scaling factor can be used in time domain as well. So because this is periodic, and in that case are equally time and frequency, both the domains it can be used. In that case 1 by root 2 of n1 n2 product here, and in the time domain also 1 by root 2 n1 n2, or use it in the frequency domain. That is all, that would also suffice. So the scaling, you should be careful that where we are using this scaling. And then the case of periodic convolution, we take an example that linear convolution in 2D we had done, and we have performed this 2D convolution through 1D convolution if it is separable, the sequence. Now the periodic convolution we see for the sequence, that is x tilde n1 comma n2, where this is the sequence 1 1 1 1 0 0. So this two values are 0, that's why it is not filled, and but the sequence exists in 0 0 1 0 2 0 and 0 1 and other values. So this is having the pattern, repeated pattern, and similarly y tilde n1 comma n2 also has 1 2 3 4 5 6. So this is, so we are going to convolve these two sequences. Then what should be the procedure to be followed? So for periodic convolution or the circular convolution, so here the x tilde will first change the index as we do in the case of linear convolution, n1 to L1, N2 to L2. So this indices are changed, and then you can see the y tilde also we can make it to L1 and L2. Similarly, this can be changed to L1 and L2, and then flip it to accommodate in the summation minus L1 minus L2, where N1 and N2 are 0. So if we flip it, this would be 1 here, and this one 1 comma 0 will become here minus 1 comma 0, and 2 comma 0 indices will become minus 2 comma 0, and this 0 comma 1 is becoming 0 minus 1, and you can see the 5 1 1 1 is minus 1 minus 1, and 6 becomes this here. So this is the flipped sequence now. Now we to get the first indices, that is the flipped sequence, and this now if you see in the linear convolution, what we did, we just see the common points, common indices, and multiply and sum it over. Whereas here this is a periodic or circular convolution. What we are supposed to do, this is periodic with respect to 3 in n1 and 2 in n2. This is n2 here. So 3 and 2. So this sequence should not exceed that 3 2. If you recall that in the 1D we have done in one of the examples, if it is the sequence is not, it should be made it to the period mod function. So to calculate this mod of this, so what we do, this is 0 comma 0, there is no issue in this, and this is having this minus 1 comma 0. So minus 1 comma 0, which is here 3 and minus 1 and 0, this factor is not going to be a problem. So minus 1 needs to be addressed, so to bring it to the 3 by 2 formation. So in this case, this becomes 2 comma 0, that this 2 signal is becoming 2 comma 0, and 3, if we say this is 1 comma 0, similarly this is minus 1 here and minus 2 comma 0. So minus 2 comma 0, the index is 3 minus 2, that becomes 1 comma 0. So this is how we change it from the pattern which is to be in the periodic convolution. And similarly this 4, you can see this this y2 is minus y2 or n2 is minus 1 here. So 0 comma minus 1. Okay, so this needs to be here, this is not a problem, 0 and 2 minus 1, so that becomes 1. So 0 1, so this is becoming 0 1. Okay, so we have to bring it to this, and similarly 5 here is minus 1 and minus 1, so this becomes 5 here, and similarly this word goes to this. So we have to bring it to the condition within this 3 by 2 the n1 and n2. So if this is the case, the mod function is applied. So on the sequence, the flipped sequence, as in the linear case, will not be computing shift and add or multiply and the individual indices and the positions of each x and y and then add it. Instead of it, we have to bring it to the next step, wherein we have to take care of this n1 n2 periodicity. So the signal what you get now, you can have the multiplication of the indices. So that would result in, that is equal the multiplication and sum it over L1 should vary from 0 to 2 only, not more than that, and then here 0 to 1. So similarly this is 0 to 2 and 0 to 1. So the other sequence also made it of a same length, so x and y. So if you recall in this circular convolution, so this is made it of equal length. Now multiplying the position 1, this position 1, and this would result in 3, and this would result in 2, and this would result in 4. So the summation comes out to be 10. So wherein we got the convolution of this is two sequences n1 and n2 0 0. Suppose we take that as z 0 0 is this value, the circularly convolved value. So similarly for the get other one, the other sequence x tilde of L1 comma L2, this is there, and flipped sequence for 1 comma 0. So z of we try to compute for 1 comma 0. So in this case, again the flipped sequence, you can see n1 should be 1. So shifted here, you can see the shifted sequence compared to the previous only flipped sequence. Now after shifting 1 comma 0, make the mod function. So the mod function will result in this two. Okay, there is no issue on this indices, and whereas this indices minus 1 comma 0, 3 would push to here, that is 2 comma 0, and similarly 6 would go here and 5 would come here and then 4 would come here. So this is to make the indices 3 into 2. So for example, we saw that this is for 3 minus 1 comma 0. So this should be 3 minus 1 comma 0, that going to be 2 comma 0. Similarly, you have to take the indices of the ones which are not of 3 by 2, and if it is n1, that is capital N1 minus the sequence value, comma capital N2 minus the sequence value, if the sequence indices exceeds that 3 by 2 only. Otherwise, you need not do the mod function in this case. So these two signals doesn't need any change to 1 1, but the other dots needs that 3 by 2. So this is pushed, and then now you can find this common indices 1 into 5 and 1 into 2, 1 into 1, and then 1 into 3. So sum it up together, get 11. So that's the periodic convolution, this value of y 1 comma 0. So similarly, for the case of 0 comma 1, that is z tilde of 0 comma 1. So the flipped sequence, it's a 0 1 is now, it is shifted up. The flipped sequence is, you can see it is n2 direction, it is flipped up, whereas that in the previous case it was 1 side right, and this is shift up, n2 is 1 here. So now this indices, this 1 and 4 doesn't need any change here, that's fine, and 2 is pushed to here. So check the indices and bring it to 3 by 2, and then this one is here and 5 is pushed to here, and similarly 6. So this is the mod function applied y, and now find the common areas 1 into 1, 1 4 and 1 6 and 1 5. So you get it, the summation as 16. So this would result in 16 over here, that is 0 comma 1. So similarly, we'll continue for the 1 1 case. So you can see the flipped sequence, right shifted ones and then up shifted ones, that is in this direction and in this direction. So then we find the mod function. So here that is 2 and 5, 4, 2 1 5 1 4. So these two have, I mean 4 of them doesn't need any of this, whereas 3 should be pushed and 6 should be pushed because this is in the negative indices. So now we can find the common one, that is 1 2 and then 1 5 and 1 4 and 1 6. Multiply them and add this together, get 17, which is the 1 1 case, that is z of 1 comma 1. So similarly, for the case of n1 2 comma 0, z 2 comma 0, we would like to find out the convolution here, that is circular convolution. The flipped sequence is 2 times shifted in this direction. So and then find the mod function. So 3 2 and 1, so there is no indices change, whereas these signals needs to be changed. So 6 is pushed to here, if you bring it to 3 by 2 periodicity, and then 6 5 and 4 is pushed above, and now check the corresponding indices and multiply them, get the, and add it to get the 12. So this is for 2 comma 0, where you get z tilde 2 comma 0 is 12 here. So similarly, the one more one is 2 comma 1. So this is the one, n1 is shifted twice and then n2 is shifted up, so from the flipped sequence. So this, and then apply the mod function. Here you can see all of them are in the indices of n3 to, that is n1 to n2, that is 3 by 2. So there is no need to change here, just multiply these sequences at the respective positions and add it together, so get 18. So this is how we have get, this is 18 now. This is z tilde of 2 comma 1. So this is a convolved sequence, complete sequence. We got it through this, the periodic convolution or the circular convolution. You see the resultant length of this sequences, this is also 3 by 2. Okay, it's not like the linear convolution, the length varies up to n1 minus 1 plus n2 minus 1 and so on. So n1 plus n2 minus 1. So that's the length of the linear convolution, whereas here this would be the convolution length remains same. So this is how we have to perform the periodic convolution or the circular convolution in 2D sequences. We have shown that in 1D as well, so you can apply the same thing here as here also. But the third step which is required is important to bring the flipped sequence, and then the signal points which are out of this n1 n2 needs to be brought back to n1 and n2 using the mod function. So now coming to the next property, that is a separable sequence. So in the separable sequence, we have already done that quite a lot of the convolution operation, and we'll also do the DFT thing, how we can simplify that 2D DFT into 1D DFT. So here the product of x tilde, it could be written in terms of the product of two sequences, that is n1 and n2. So if that is the case, taking the Fourier series would result in x tilde of k1 comma k2 and its individual sequences. Okay, so the assumption of this DFS is n1 periodicity and n2 here n2 periodicity, then length is n1 and n2. In that case, this can be separated. So it becomes easy that in the Fourier DSFT we have shown that if this can be written in terms of two sequences of product, then its frequency domain also, the x and x2, x1 and x2 can be a product of two sequences in the frequency domain. So that we have done for DSFT. This is for the DFS, where this signal is periodic. This pattern is even repeating, that in the previous example 3 by 2 n1 n2 is going to be repeating in the n1 direction and as well as n2 direction. So if this tilde implies that it is a periodic sequence in 2D. For a shift sequence, the property, if a shift delay of n1 and n2, so results in a multiplication of e power minus j 2 pi k n1 m1 the delay, and then similarly m2 delay in n2. So this we had seen in 1D as well. This simply extended to 2D of this in frequency domain. This is causing the phase change. Okay, so the delay. So if you take the case of initial value and that DC value theorem, in which that x tilde, we want to find out n1 and n2 0 0 what is the value at initially. So compute the coefficients of this, and the n1 take the this would give the case of initial value, and if we want to have the DC value and then sum it over all the samples from n1 to n2 of this particular period and get this average value, that is x tilde, which is nothing but the DC value. So if we, from that DC value, if you want to know the initial value, so you can get, sum it over from k1 to k2, n1 to n2 here, and use the equation and then get the initial value. So initial value can be obtained from the coefficients as well as from the coefficients, or if you know the sequence, then DC value can be obtained. Now, the Parseval's theorem is important to know that energy is preserved in both the time domain and the frequency domain. So the case of the star implies the complex conjugate. So whatever the x and y, if sum it over in the two dimensions n1 and n2, so the product also here will be equal. So this is also the energy is preserved. This is a second form of Parseval's theorem. Instead of two different sequences x and y, so you can have the same sequence x tilde, its energy is the absolute square. This is the energy formula within 2D, and 1D we had done energy signal and power signal, and we computed the energy of a particular signal. This is a 2D sequence energy signal, and it's equivalent to the coefficient squares and the number of n1 and n2 to be divided here. So these two are equal. That means the energy in the time domain, it's equivalent to the energy in the frequency domain. Those are distributed among the coefficients. That's the Parseval's theorem. And we take some examples of 1D DFS. So we have seen that x of n is cos n pi by 3 plus pi. So if this is a 1D sequence, and what is the frequency of it? It is pi by 3 to equal to 2 pi by n. Now, if how do we express this in DFS? Okay, so taking this x of n, so to get the DFS, what we do is we get the coefficients from the analysis equations. But we can use the synthesis equation as well. So x of n can be written as in e power j and e power minus j theta, e power j theta plus e power minus j theta by 2, and where theta is this n pi by 3 plus phi. So now this is the expansion of this x of n. If we use the trigonometric Fourier series, that we can also splitted here. This these things are splitted, two of them. Phi is here and n pi by 3 is here. So similarly n and n. So the coefficient of so what is the coefficient here? These are the coefficients here, right? So we'll compare it with the DFS equation. What is the periodicity for this case? So pi by 3, which is 2 pi by n, so n is 6. So the periodicity turns out to be 6. So x of n, now to the analysis, from the analysis equation, what you get is that coefficients, and the synthesis equation, that if you have the coefficients or you can write it in terms of sum of this. So this is x of n. So in the synthesis equation, how do we get the coefficients? That's what, how do we represent it? Is the sum of the sinusoids. So in the trigonometric case, e power j 2 pi k n by n. So because n is 6, k is varying from 0 to 5 here, ck, and r it can be from -2 to 3 as well. This is the periodicity of the sequence here. So now get this x of n, which is expanded, k varying 0, k1, and then here k2, and then k3 and k4, as well as k5. Okay, so similarly these k values are substituted here, and this is the equation. Now if we compare it with the previous equation, so c1 is coming to be, this is pi by 3n, and you get the coefficient c1 as this, and you have c minus 1 also, that is, if we write it in terms of -2 to 3, this is -1. So the other coefficients doesn't match. Okay, so for k equal to 1, that is, it has only fundamental, and that's also reflected in k minus 1, and other indices k minus 2, 0, 2, 3, this is 0. So these coefficients can be directly obtained from expanding it with the trigonometric Fourier series. So the magnitude and phase spectra, this is the magnitude spectra, that is 1 by 2, and here is the phase spectra. Phase spectra, this 1 by 2 here we got, and in case this 5, phi is not known, just returning says phi, that phi is whatever the phi may be, this could be plotted in the phase spectra as well. So it is even symmetric, and this is odd symmetric, as we had seen in the other cases as well. So now getting this 1D DFS to 2D cases. So consider the sequence x tilde, that is, you can see the pattern of 1, 2, 3. This is 0, 0, and here is 1, 0, and 0, 1. So this is the pattern which is repeated here, n2 direction as well as n1 direction. So this is we say both periodic, in row wise as well as column wise periodic, and in the this is extended to infinity in this direction, n2 and minus infinity to plus infinity, similarly n1 minus infinity to plus infinity. This is shown for a certain range only, but this signal is extended. So for this case, so what is 0, 0 is 1, and 1, 0 is 2, and then 0, 1 is 3, and 1, 1 is 0. So use the n1 and n2, if we take, it's clear, very clear that n1 it is 2 and 2. Okay, so from this, so from the equations, how do we get the DFS? So DFS is x take this signal and e power minus j 2 pi k1 n1 by n1 k2 n2 by n2. So n1 n, this is 2 minus 1, 0, 1, and 0, 1. There are two values only. So we'll substitute them, k1 0 and k1 1, k1 0 and k1 1 for this value. So this equation is valid with the definition of k1 and k2. k1 and k2 varying from 0 to n1 minus 1, and k2 similarly 0 to n2 minus 1. So this is for one period. We have taken it for one period. So computing these coefficients with this x tilde k1 k2, we substitute either here, we get this in terms of k1 and k2, n1 and n2 values substituted. So get the x tilde k1 equation. So this is the equation which we get for k1 and k2. This is going to be the -1 e power minus j pi. So simplifying the steps are shown here, x tilde 1, 2, and this. So now varying this 0, k1 and k2 are 0 and 1. So 0, 1, substituting in the expression of 0, and this 2 becomes 1, 1, 1. So we get 6, and 1, 0 minus 1 and 1. So this is going to be 2, and then similarly this is 0, and then here we have minus 4. So 6, 2, 0 and minus 4 are the values we get, 6, 2, 0 and minus 4. So with this we have seen the properties of discrete Fourier series, where we call this discrete Fourier series as DFS, not like DTFS in 1D, because time parameter is dropped in this 2D, because it's a DTFT is called DSFT, whereas this DTFS is called this DFS. So we have seen the properties of it, important properties, and how to do the circular convolution or the periodic convolution, which is simply the multiplication of this DFS in 2D of two sequences. If it is convolution in the time domain, it's going to be a multiplication in the frequency domain, or if it is a multiplication in the time domain, and it's going to be a convolution in the frequency domain. So in both the ways we can do this periodic or circular convolution, and we have seen an example of computing this DTFS for one sequence 1D, and we have also extended that to 2D DFS. We'll continue this thing, and how to use the scaling that has been given in these examples. Either scaling can be used in this. We stick to one of the equations which can be used in synthesis equation instead of analysis equation. Okay, so we have used all of them in the synthesis equation and the scaling, and so n1 n2, the scaling factor doesn't involve in the analysis equation. So we would continue with the how to code them, how to get these details in the MATLAB for the examples what we have seen so far. Thank you.